both 6 and 15 to divide our number. So if we just use 2 times 3 times 5, which is 30, we know that 2 times 3 will divide it, and 3 times 5 will also divide it. And we won't be able to get a denominator any smaller because we need the factors 2, 3, and 5 in order to ensure both these numbers divide it. Once we have our least common denominator, we can rewrite each of our fractions in terms of that denominator. So 7/6, I need to get a 30 in the denominator, so I'm going to multiply that by 5 over 5. I multiply by the factors that are missing from the current denominator in order to get my least common denominator of 30. For the second fraction, 4/15, 15 times 2 is 30, so I'm going to multiply by 2 over 2. Now I can rewrite this as 35/30ths minus 8/30ths, and now that I have a common denominator, I can just subtract my two numerators, and I get 27/30ths. If I factor, I can reduce this to 3 squared over 2 times 5, which is 9/10. The process for finding the sum of two rational expressions with variables in them follows the exact same process. First, we have to find the least common denominator. I'll do that by factoring the two denominators. So 2x plus 2 factors as 2 times x plus 1. X squared minus 1, that's a difference of 2 squares, so that's x plus 1 times x minus 1. Now for the least common denominator, I'm going to take all the factors I need to get an expression that each of these divides into. So I need the factor 2, I need the factor x plus 1, and I need the factor x minus 1. I don't have to repeat the factor x plus 1, I just need to have it one time. And so I will get my least common denominator 2 times x plus 1 times x minus 1. I'm not going to bother multiplying this out. It's actually better to leave it in factored form to help me simplify later. Now I can rewrite each of my two rational expressions by multiplying by whatever's missing from the denominator in terms of the least common denominator. So what I mean is I can rewrite 3 over 2x plus 2. I'll write the 2x plus 2 as 2 times x plus 1. I'll write it in factored form. And then I notice that compared to the least common denominator, I'm missing the factor of x minus 1. So I multiply the numerator and the denominator by x minus 1. I just need it in the denominator, but I can't get away with just multiplying by the denominator without changing my expression. I have to multiply by it on the numerator and the denominator, so I'm just multiplying by 1 in a fancy form and not changing the value here. So now I do the same thing for the second rational expression. I'll write the denominator in factored form to make it easier to see what's missing from the denominator. What's missing in this denominator compared to my least common denominator is just the factor 2. So I'll multiply the numerator and the denominator by 2. Now I can rewrite everything. So the first rational expression becomes 3 times x minus 1 over 2 times x plus 1, x minus 1. And the second one becomes 5 times 2 over 2 times x plus 1, x minus 1. Notice that I now have a common denominator, so I can just add together my numerators. So I get 3 times x minus 1 plus 10 over 2 times x plus 1, x minus 1. I'd like to simplify this, and the best way to do that is to leave the denominator in factored form, but I do have to multiply out the numerator so that I can add things together. So I get 3x minus 3 plus 10 over 2 times x plus 1, x minus 1, or 3x plus 7 over 2 times x plus 1, x minus 1. Now 3x plus 7 doesn't factor, and there's therefore no factors that I can cancel out. So this is already reduced as much as it can be. This is my final answer. In this video, we saw how to simplify rational expressions to lowest terms by factoring and canceling common factors. We also saw how to multiply rational expressions by multiplying the numerator and multiplying the denominator, how to divide rational expressions by flipping and multiplying, and how to add and subtract rational expressions by writing them in terms of the least common denominator. This video is about solving quadratic equations. A quadratic equation is an equation that contains the square of the variable, say x squared, but no higher powers of x. The standard form for a quadratic equation is the form ax squared plus bx plus c equals 0, where a, b, and c represent real numbers. And a is not 0, so that we actually have an x squared term. Let me give you an example. 3x squared plus 7x minus 2 equals 0 is a quadratic equation in standard form. Here a is 3, b is 7, and c is minus 2. The equation 3x squared equals minus 7x plus 2 is also a quadratic equation. It's just not in standard form. The key steps to solving quadratic equations are usually to write the equation in standard form and then either factor it or use the quadratic formula, which I'll show you later in this video. Let's start with the example y squared equals 18 minus 7y. Here our variable is y, and we need to rewrite this quadratic equation in standard form. We can do this by subtracting 18 from both sides and adding 7y to both sides. That gives us the equation y squared minus 18 plus 7y equals 0. And I can rearrange a little bit to get y squared plus 7y minus 18 equals 0. Now I've got my equation in standard form. Next, I'm going to try to factor it. So I need to look for two numbers that multiply to negative 18 and add to 7. Two numbers that work are 9 and negative 2, so I can factor my expression on the left as y plus 9 times y minus 2 equals 0. Now, anytime you have two quantities that multiply together to give you 0, either the first quantity has to be 0 or the second quantity has to be 0, or I suppose they both could be 0 in some situations. This is really handy because that means that I know that either y plus 9 equals 0 or y minus 2 equals 0. So I can, as my next step, set my factors equal to 0. So y plus 9 equals 0 or y minus 2 equals 0, which means that y equals negative 9 or y equals 2. It's not a bad idea to check that those answers actually work by plugging them into the original equation. Negative 9 squared, does that equal 18 minus 7 times negative 9? And you can work out that it does. And similarly, 2 squared equals 18 minus 7 times 2. In the next example, let's find solutions of the equation w squared equals 121. This is a quadratic equation because it's got a square of my variable w. I can rewrite it in standard form by subtracting 121 from both sides. Notice that a is equal to 1, b is equal to 0 because there's no w term, and c is equal to negative 121 in the standard form aw squared plus bw plus c equals 0. Next step, I'm going to try to factor this expression. So since 121 is 11 squared, this is a difference of two squares, and it factors as w plus 11 times w minus 11 is equal to 0. If I set the factors equal to 0, I get w plus 11 equals 0 or w minus 11 equals 0, so w equals minus 11 or w equals 11. In this example, I could have solved the equation more simply. I could have instead said that if w squared is 121, then w has to equal plus or minus the square root of 121. In other words, w is plus or minus 11. If you solve the equation this way, it's important to remember the plus or minus, since minus 11 squared equals 121, just like 11 squared does. Now let's find the solutions for the equation x times x plus 2 equals 7. Some people might be tempted to say that, oh, if two numbers multiply to equal 7, then one of them better equal 1 and the other equals 7, or maybe negative 1 and negative 7. But that's faulty reasoning in this case, because x and x plus 2 don't have to be whole numbers. They could be crazy fractions or even irrational numbers. So instead, let's rewrite this equation in standard form. To do that, I'm first going to multiply out. So x times x is x squared, x times 2 is 2x, that equals 7, and I'll subtract the 7 from both sides to get x squared plus 2x minus 7 is 0. Now I'm looking to factor it, so I need two numbers that multiply to negative 7 and add to 2. Since the only way to factor negative 7 is as negative 1 times 7 or 7 times negative 1, it's easy to see that there are no whole numbers that will work. So there's no way to factor this expression over the integers. Instead, let's use the quadratic equation. So we have our leading coefficient of x squared is 1. So a is 1, b is 2, and c is minus 7. And we're going to plug that into the quadratic equation, which goes x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Different people have different ways of remembering this formula. I'd like to remember it by singing it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But you can use any mnemonic you like. Anyway, plugging in here, we have x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 7. It's important to remember the negative 7 there, all over 2 times 1. Now 2 squared is 4, and 4 times 1 times negative 7 is negative 28. So this whole quantity under the square root sign becomes 4 minus negative 28, or 32. So I can rewrite this as x equals negative 2 plus or minus the square root of 32 all over 2. Since 32 is 16 times 2, and 16 is a perfect square, I can rewrite this as negative 2 plus or minus the square root of 16 times the square root of 2 over 2, which is negative 2 plus or minus 4 times the square root of 2 over 2. Next, I'm going to split out my fraction as negative 2 over 2 plus or minus 4 square root of 2 over 2, and then simplify those fractions. This becomes negative 1 plus or minus 2 square root of 2. So my answers are negative 1 plus 2 square root of 2 and negative 1 minus 2 square root of 2. And if I need a decimal answer for any reason, I could work those out on my calculator. As our final example, let's find all real solutions for the equation 1/2 y squared equals 1/3 y minus 2. I'll start as usual by putting it in standard form. So that gives me 1/2 y squared minus 1/3 y plus 2 equals 0. I could go ahead and start trying to factor or use the quadratic formula right now, but I find fractional coefficients kind of annoying, so I'd like to get rid of them by doing what I call clearing the denominator. That means I'm going to multiply the whole entire equation by the least common denominator. In this case, the least common denominator is 2 times 3, or 6. So I'll multiply the whole equation by 6. I have to make sure I multiply both sides of the equation, but in this case, 6 times 0 is just 0. And when I distribute the 6, I get 3y squared minus 2y plus 12 equals 0. Now I could try to factor this, but I think it's easier probably just to plunge in and use the quadratic formula. So I get x equals negative b, that's negative negative 2, or 2, plus or minus the square root of b squared, minus 4 times a times c, all over 2a. Working out the stuff under the square root sign, negative 2 squared is 4, and here we have, let's see, 144. So this simplifies to x equals 2 plus or minus the square root of 4 minus 144, that's negative 140 all over 6. Well, if you're concerned about the negative number under the square root sign, you should be. We can't take the square root of a negative number and get a real number as our answer. There's no real number whose square is a negative number. And therefore, our conclusion is we have no real solutions to this quadratic equation. In this video, we solved some quadratic equations by first writing them in standard form and then